So simplify the following rational expressions. Well, simplifying rational expressions is like simplifying ratios. This is essentially an exercise in finding common factors and canceling. And let me just point out, well, you've done this before with numbers. Like, so for example, if I just said simplify 12, number 24 over 15, and I said reduce that or simplify. It's like that's a rational expression. Simplify it. What you're doing, even if you could do it in your head, what you're like, ooh, let's think about this in terms of some common factors. 24 I can write as 3 times 8. 15 I can write as 3 times 5. Since I have a common factor on the top and the bottom, I can essentially multiply this by 1/3 over 1/3, which really comes down to like 3 over, or actually, sorry, I'm going to rephrase that. What you're really doing is kind of writing this as rewriting this expression factored as 3 over 3 times 8 over 5. And once you do that, 3 over 3 just turns away to 1, and so you get 8/5. But you can think of that as like the 3's canceling. But that's why the 3's canceling works. And so even though, so this is how it works, which is numbers. Every one of these other problems in 27 is that same idea, is find the common factors and cancel to simplify. So here, we have 10x over 25. Well, there's no common x factors in the top and the bottom, but there is a common number. So we can rewrite this as 2 times 5x, and this is 5 times 5. Sorry, 2 times 5 times x. And so what you're doing here is we see that there's a common 5 that can be divided in the top and the bottom. So those 5's will cancel, and you're left with 2x over 5. If this, for example, had been 10x squared over 25x, it would have been a similar kind of idea. This would have been 2 times 5 times x squared over 5 times 5 times x. Those 5's would still cancel, but now we also have an x squared over an x, and you can subtract those exponents. Remember, x squared over x equals just x, because you subtract exponents by canceling, and that would have gone away. This would have turned into a 1, and you would have gotten actually the same answer, 2x over 5. The extra x in both the numerator and denominator didn't change the answer, but I just wanted to go through what happened with variable canceling. C here, you have to remember how to factor these these binomials. So you're finding two numbers that, now again there's an implied 0D here, so two numbers that add to 0 and multiply to -4. Well, if you think about that, though, you get -2 and 2, and that's going to be how we're going to factor this. So we're going to keep the numerator as is, and we're going to rewrite the denominator in its factored form, which is d minus 2, d plus 2, and now we can see we have a common factor at the top and the bottom. We're going to cancel those out, and we're left with 1 in the numerator, d minus 2 in the denominator. B, same procedure. We got to factor and cancel. So the question is, well, this doesn't look like this is how do I factor that numerator? And we can see that there's a 3 in both terms, and so that's the key to this one, is to take out that 3. And you can also probably see that there's a c plus 11 in the denominator, so that might suggest what you might end up with in the numerator, but you still got to just go through the factoring because it doesn't always work that way. You could see that, like, if I were to redistribute the 3, I'd get 3c plus 33, which is that original numerator. So that's why the factoring, the 3 comes out, works. And then once I've done that, I get c plus 11 in both, and all I'm given is 3. I guess just to see that this does in fact work, let's say if we would have picked c equals 1, we would have gotten 3 plus 33 in the numerator, 1 plus 11 in the denominator. This would be 36 over 12, which equals 3. So you can see, like, just for an example, representative value of c, C almost like didn't matter in this. Same thing here, we got a factor. Now we just got to remember how to factor this thing. We need two numbers that add to -6, multiply to 8. So, you know, like A plus B has to equal -6, A times B has to equal 8. Go through different factor pairs and you would hopefully quickly see that -8 and 2 are the correct answers there. So, okay, so I had a little brain spasm there. Sorry about that. -8 and 2 are definitely not it. It's two numbers again. So if we have -4 and -2, it will satisfy the criteria. So -4 plus -2 is -6. Multiply those two, you get +8. So now we can go ahead and factor y -2, y -4, all over y -2. And conveniently we have these common factors, and so this term simplifies to simply y -4. Question 28, this is the Algebra 2 version of adding fractions. Let's just remind ourselves how that would work with some simple numbers here. If I had 3/4 plus 7/4 and asked you to add those, you would hopefully recognize that, well, I have some common denominators here, so all I really have to do is add the numerators. 3 plus 7 equals 10/4, which you could reduce that to 5/2. But you think about like pizza or something. If I have 3/4 of a pizza and 7/4 of a pizza and I jam them all together, I have 10/4 of a pizza, which is the same thing as 2.5 pizzas or 5/2. If I have to add fractions and they don't have a common denominator, like if I change this to 7/3 instead of 7/4, I can't simply combine at that point. I need to have a common denominator base, and so the goal here is to create a common denominator by finding the least common multiple of these two things. So like 12 would work, and then I have to, when I do that though, I have to multiply each expression by its corresponding funny form of 1. So the way I convert 3/4 to 12 is to multiply it by 3/3. The way I convert 7/3 to 12 is to multiply it by 4/4. And so 3 times 3 over 12 is 9/12. 7 times 4 is 28 over 12. Now that I have my common denominator, I can go ahead and just add those numerators to get 37/12. And so that would be the answer to this simple addition problem. So this is the idea that will get applied, but just in the context with expressions. So for A and B, or A and C here, I'm sorry, you can see that I have a common denominator. It's an expression, but it's x minus 3. So that becomes a relatively simple idea then. I just can use the common denominator. I'm going to add the numerator. So I'm going to add the 9 plus the x plus 1. And then finish simplifying that up in the top. 9 plus x plus 1. The 1 and the 9 can combine to get x plus 10 all over x minus 3. So see how I've started with two rational expressions and I converted it into one. That's the goal here, is just to, how do you work with these adding and subtracting. Here, C is another situation where you just have the same common denominator. So I can go ahead and just start with that. I don't have to do any of this funny form of 1 stuff. I have this fraction is 5. Now, you have to be a little careful there. We're subtracting. So if I'm subtracting 2, I have to make sure to subtract those numerators as well. This is just going to be -4 over y squared plus 1. Okay, let's move on to B and D here. Now we have a situation where I don't have the same common denominator. So if goal 1 should be to get us to the same one, I'm just going to rewrite this as 5x plus 4 times something which I don't know yet, and then 2 over 5x times something which I don't know yet. And I need to find a denominator that both of these things will go into. So I know I'm going to need an x in each of them. And then the least common multiple of 4 and 5. If I just go through the multiples of 5, 10 won't work because 4 doesn't go into it. 15 doesn't work. 20. So 20 is the first multiple of 5 that 4 will go into. 20x will work here. So I need to put 20x times 20x because these adjustments here need to be all equal to, the funny form of 1. And now that I think about it, this is the wrong fraction here. This is both the wrong fractions. Sorry, throwing you off here. I want the result to be 20 over x. So I need to figure out what I need to put here. So to get 20 over x on the bottom, this is going to need to be 5x. So that when I do 4 times 5x, I'll get 20x. And then this will just be 4 over 4. So that when I multiply these, I get 20 over x. Sorry about that if that threw you off. Hopefully you recognize that was wrong, and that means you're actually understanding this better than you think. So now I have 20x in this denominator, and then I multiply these top here. This is 25x squared, and then I have 20x in this denominator, 5x times 4, 2 times 4 is 8. Now I have the same common denominator, and I can add those numerators, 25x squared plus 8. Same thing here, same process. We're going to write these out, and then we need to figure out what fraction is going to go on each one of these so that we can get a common denominator. Well, we have an x and an x squared, so we know x squared will be part of our least common multiple, and then 2 and 5. So 5 is not divisible by 2, but the next multiple of 5, 10 is. So 10x squared is going to be the common denominator we're looking for. So then the question is, for each one of these, what do I have to multiply by to get me to 10x squared? Well, 2x goes into 10x squared. I'm going to need a 5 and another x. 5x squared to get to 10x squared. That's just going to be simply multiplying by 2. So now you can see, actually I'm going to erase this here. So this will be 35x over 10x squared minus 2 times 2 is 4 over 10x squared. I have my common denominator, 35x minus 4. So I've accomplished my objective of simplifying this to one common expression by using that same kind of technique that we used for simple